There we go. Okay, we're recording now. Before we get started, are there any questions about anything so far? It gets rather boring just talking at you, so if you have a question, please ask the question. Also, no one came to office hours today. I get so lonely. Look at me, I'm hiding in my basement. It's very lonely down here, and it's cold. I had to put on a sweater. All right, so by the way, I do want to take a moment to thank everybody for your patience for the switch to the online all of a sudden at the end of the semester. Could you go over how to make the save catalog function for assignment 4 part 2? Well, I can't go over it too much, but what I can do is go over how to save stuff to a file. Okay, I will go over that a little bit, so I will. Thank you for asking that question, and I'm so starved for questions that I will, in fact, answer a question regarding assignment 4. I will get to that, but yeah, I do thank you for the switch to online and your patience with this. Also, patience with me figuring out how to use Blackboard Collaborate. I don't know, if I ever do online again, I think I got to figure out a better system, but that's okay for now. Also, I did make a lot of errors last time. I don't know why. Scatterbrain figuring out online. I kept messing up the greater than, less than thing. So hopefully that wasn't too abrasive and you still got the spirit of the idea of selection sort. That was the one we did, right? Selection sort? No, it was insertion sort. We'll talk about selection sort today. Before we talk about the question that was just asked about assignment 4, are there any questions regarding, oh, I do remember another thing I needed to make an announcement about, and I will do that just after this bit. Okay. Are there any questions about the exam? The exam will be released next Wednesday. I'm just curious if there's a question right now about the exam that we can answer and get out of the way. And if people are typing that into the chat, do so. Also, feel free to just turn on your mic and ask the question, I guess. What else? All right. I got to have another little discussion about cheating. So I want to reinforce the fact that this year has actually been really good for not much cheating taking place in 161, or just a computer science intro CS in general. Intro CS in general typically has a very high cheating rate. So the fact that we don't have that much is actually a really good sign. I mean, obviously we want no cases of it, but, you know, call a win a win. But the reason I got to bring this up again is there's been a lot of discussion within the university and a lot of discussion outside the university and just about universities in general. So the cheating is obviously not unusual at university. We typically catch it, but of course this year is a little bit different, right? And it's understandable that it's different, but that doesn't mean the expectations and requirements and responsibilities, they don't change. There's still the bar that we set that has to be met. And cheating has gone up a little bit. And you may have even seen the thing in the news about how there was a leak about over 100 people getting caught cheating on an intro calc class at UBC or something. That's a big number. And I wouldn't be surprised if there's a lot of other classes that have the same thing at other universities. And it's just, these are the ones we're hearing about. Because of all this discussion, there is a lot of extra vigilance on cheating this year from the professor's side and the institution side. Because the final exam for this course is like a take-home, you might feel as if it's much easier to cheat. I can guarantee you it won't be. I can guarantee you that this year might even be a harder year to cheat, just by how things are playing out. I actually just finished a meeting with some of the academic integrity officers on campus, just finished, and then I ran to this class. And by ran, I mean clicked a couple of buttons to hop on over to collaborate. But there's going to be very, I don't know the word I want to use, for lack of a better term, very strong, there's going to be a very strong enforcement and very strong application of strong decisions of what to do about individual cheating cases. So I know I'm giving you this little talk, and of course, no, this is not going to apply to anyone in here, right? Because none of you are going to cheat. This is a useless conversation I'm having, but I'm going to say it just so the warning's there. You've been warned. I don't even know how many times. We can go back and watch the YouTube videos I've talked about not cheating. Just go watch the first lecture, and you'll hear me rant about cheating. I will catch you, and the university is just waiting to, not just this university, universities are just waiting to apply and put down that hammer of justice, I guess. So don't do it. I know you weren't going to do it, but don't do it. Any questions about cheating? And don't worry, I've been doing this long enough, and the universities have been doing this long enough, that we know cheating from just a dumb coincidence. But you also have to be very clear on what cheating is. And I'm going to clarify a couple of things right now, but none of this is new information to you. This isn't new. I know you know these rules. These have been the rules since you were, I don't know how big, how old. You were really young, you learned these rules about cheating. Cheating is not just, oh, I copied someone else's notes. It's also, you let someone look at your notes. You let someone look at your stuff. That's cheating. That's part of it. That's academic misconduct. And you'll get nailed for that. So just don't do anything you know you're not supposed to do. If anyone is going to not cheat, it's going to be the four, yeah, that's what I mean, right? That's what I mean, the 4 people that actually show up to the class of how many students? You're right. So this is, again, this doesn't apply to you. So hopefully those that will watch these videos later will this will resonate with them, if, you know. I also am amused at, like, the number of students I get. I mean, this is just worth a laugh. The number of students I get, you know, they'll email me and they'll say, like, oh, you know, it's the day before the assignment's due. I didn't come to any of your office hours, but, you know, I went through all the lecture. I went through the notebook. I watched all your videos, every second of them, and I'm still stuck. Okay, if you're still stuck, I'm happy to help. But don't tell me you watched all the videos, because YouTube gives me analytics on views and watch time and who's what, like not who's what, but like how many people have watched the different parts of the videos. So I know that with the number of people saying, oh, I've watched all the videos, I know that can't possibly be correct based on the statistics I get from YouTube. But anyways, they're there if you need them, so make use of them. There's one last thing I suppose I'll bring up before I go talk about that question that Kimberly asked, is I sent an email out yesterday, and if it applies to you, it's very important that you reply to that email. I've heard from a number of students that they would take or potentially even consider taking 162, but the problem they've got is it's got a conflict with another course that they need to take, and therefore they can't take the course. If that applies to you, or if that applies to someone you know, have them contact me, reply to that email I sent out and copy the chair, because it's important for us to get a sense of the numbers, because once we get a sense of the numbers, we can make proper decisions going forward. So be sure to do that. What else? Okay, so yeah. Could we go over how to make save catalog function for assignment 4 in part 2? All right, I'm going to share my screen. How do I do this? Right, share application screen. Sure, we'll do this. Welcome to Looking into Infinity. And here we go. This was sorting. Let's just go back. Whoop, CSI. Ooh. Assignment 4. Save catalog, part 2, add country, delete, find, pointer. Okay, but before anything else, I want to be very clear. This is the only assignment 4 question I will answer today because it is lecture time. Save country catalog. Okay, given a parameter, file name, write the catalog data in the file name. Okay, so here. Okay, so this is what the function definition will look like. Okay, save country catalog. Can we get the self and then file name? So this is going to be the name of the file that we're going to save. So I can call this like myfile.txt, and it should make a file called myfile.txt, and then dump all the information into that file. Did I go too far? Ah, yes. This function must return the number of lines written to the file. Oh, okay. So I guess we're going to have to constantly keep writing stuff to the file, and we'll just have to also keep track of how many lines were written to the file, and then just return that integer at the end. Not too bad. Format the file like this. Format, okay, name, continent, population, population density. So it looks like we've got these little like pipe characters, and if you can't find that on your keyboard, that's like the shift button above your, like you have to shift and hit the button right above like your enter key button and below backspace. So it looks like it's going to be the name of the country, which continent it is. Is this population? I don't remember what this is. Or is that area? Oh yeah, it says right there, population, and then population density. So it looks like we're going to have to go over our like catalog, iterate over the catalog, and for each one of those things, write this line. And I guess in that for loop, we just count how many times that for loop ran. Great. So, I mean, overall, it's not too crazy. It's just another one of those cases of, okay, there's a lot, it seems like there's a lot going on, but let's break it down. We get the file name. We're going to have to open the file and then save the file once we're done. Remember to close your file. You always have, whatever, especially when you're writing to files, you got to save them. Because if you don't, like, pardon me, close them. Because if you don't, they're going to, they won't flush, and then you won't have all the data you need in there. It'll return the number of lines. Okay, that's not bad. We just have to, like, I guess we can just get the length of the catalog, because there should be one row for each thing in the catalog, or we can count the number of times we write, but whatever. And then we're going to have to do like a, whatever the file name is, dot, write line, or whatever it is, and then this information, and then one line for each thing. So it looks like the only mystery at this stage is, how the hell do we open a file and write to it? And the good news is, we go back here, file IO. Here's how you do it. This would be the file name. And so, I mean, this is the parameter we just passed to the function, save country catalog, or whatever it was called. W for write, and then my other file. So I'm really lazy. I'm just going to go over here. Just go down here. Code, if I do this, enter. Okay, my other file dot, and what do we have here? Close, closed, detach, encoding, errors, file number, flush, is ADDI, name, new lines, read, readable, read line, read lines, seek, seekable, tell, truncate, writable, write, this looks promising, write lines. Interesting. Okay, so write. Let's just do a quick little test here. Hello. And then let's do another write. Oh. Great. And then of course I need to do my my other file dot close. Always, always, always close. Great. So we opened the file, wrote two things to it, and then went down here. Great. So let's go have a look. My files. There it is. It's saved here because it just gets put in the working directory, and this is the working directory. And there we go. That's the file. Great. Now, I mean, if you're expecting this to be on a separate line, it's not. So that's kind of annoying. But don't worry. If you ever want a new line, it's easy. Remember, it's just new line character. And if we want to get fancy, we can add like a tab character here. So let's rerun this. Run, run, run. Okay, this is going to get changed, so I have to like reopen it. There we go. Look at that. So it did hello, new line. That might be really important for the assignment. And then for whatever reason, I did a tab. It looks like tab is 2 spaces. And then we printed out world. That's all. So to go back to you, did that answer your question sufficiently? Or hopefully enough that it's pointed you in the right direction? Yes, thank you very much. All right, you're welcome. So now to what we should be doing, 15 minutes into the lecture, is learning more about sorting. So we don't want this, we don't want this, here's what we want. So we did insertion sort. And the whole idea behind insertion sort is start with an empty thing, take the new thing, put it into the sorted thing. Let me start over again. That was a horrible way of wording it. The whole idea in selection sort is, well, close that. Am I not sharing my screen? No, I'm not. Share my screen again. Nope, nope. There we go. So the whole idea is we have our list of things we want to sort. We start with an empty collection, and then for each thing in here, add it to the sorted list, starts empty, in the position it should be relative to the other things in that list. So in this example, if I'm asked to insert 5 into this list, it's got to go here, between the 3 and the 7, because we know that 5 is bigger than 3 and less than 7. So it goes there. Great. So the next one, insertion sort. Oh, wait, no, that was insertion sort. Selection sort. So here's the idea. And I want you to notice here that these are all sorting algorithms. These are algorithms that we use to sort a collection of things. And here we've just got lists, okay? And the importance here is to realize that all of these things sort the lists, but they all do it in slightly different ways. And that's what's interesting. Because you might remember I was saying, like, how many ways are there to solve a given problem? Like an infinite, great. And you may at this stage have been thinking like, oh, well, okay, what lines of code am I using? And maybe I switch the order of things, and you're thinking that's what makes a different version of your algorithm to solve a problem. And although that's true, but once we start looking at these sorts, it becomes rather obvious that, no, you can have completely different algorithms to solve the problem. Like the whole idea behind the algorithm is different, and it'll still do the same thing. So here's the idea. You give me a list called inList. I scan through the whole list to find the smallest element. I swap the smallest element with the first element in the list, or let's say 0th element if we want to be fancy. I repeat the above process for the remainder of the list, excluding the first element, and so on and so on and so on. Repeat. So here's the idea. In fact, can I find the... Insertion sort. They've got a nice GIF if I remember correctly. Here we go. Zoom in. Check this out. I like this. So it goes through. This is the first thing, right? And it finds, wait, am I doing the right one? Oh my gosh. Oh my goodness. No, we did want, not insertion, selection sort. Let's try this again. All right. So what is it doing? It goes through, finds the smallest thing, then finds the next smallest thing, and then finds the next smallest thing, find the next smallest thing. And it just keeps going like this. This is the whole idea. This is it. So, I mean, in this example, it goes through and keeps, you'll see the red thing is the smallest thing I've seen so far. And then the yellow bit is the part that's already sorted. So when we go back to start the scan, we don't need to start at the beginning, because we only need to go to the part where it's like, boom, there. We don't need to look at the first spot anymore, because we know we're guaranteed that the smallest thing is in the first spot by virtue of how this sort works, right? Because the first time through the list, you find the smallest thing and then put it at the beginning of your list. Done. We don't need to look at that anymore, because we know that is where it belongs. Okay, different areas. Okay, so this is kind of what I was talking about a moment ago. So this is very important to understand. Sorting is a problem, not an algorithm. There are infinitely many solutions for this problem, and the algorithms will always solve the problem more efficient. Some algorithms will be more efficient than others. Like, that's going to happen. And some will solve it more efficiently for certain conditions and other conditions. Like we saw last time. Remember how when the list came in already sorted, with the algorithm we looked at before, and I want to be clear, with this specific insertion sort algorithm, we saw that if the list was already sorted, it was actually really crappy. But if the list was like happened to be sorted in reverse order, suddenly this algorithm, the way it was implemented, was like really fast. Now, there's other ways I can implement the idea of insertion sort where maybe that case isn't quite true. But this is what I mean by different like starting conditions resulting in certain algorithms working faster than others. So in this case, with this implementation, the best case scenario was if we got the list in reverse order. The worst case scenario was if we got the list already sorted, which almost sounds really annoying, right? Because if the list is already sorted and suddenly that's the worst case scenario for this sort, come on, that seems silly, but whatever, it's the way it is. All right, so here is an implementation of selection sort. Point is, this is a single implementation of selection sort. I can implement selection sort many different ways, just like I could implement insertion sort many different ways, but I can implement many different sorting algorithms that are entirely different from one another to still sort. So what are we saying here? So for I in the range of the length of the list, okay, so I is going to start at 0 and go to the end of the list, so n minus 1. Min index is I, so we start with, okay, the first time through the loop, the minimum index is going to be 0. That's kind of like keeping track of like, okay, which index are we looking for the thing that belongs in it? So the first time through the loop, this is 0. That makes sense. And the next time through the loop, it'll be 1, and then 2, and then 3, and so on. And that should make sense, right? Because the first time through the loop, that's the 0. Boom, there. Next time, 1, that's the thing we want. Then 2, then 3, and so on. And then we get the minimum value, and it's going to be the value at that index. That's the smallest thing we've seen so far. Then we've got an inside for loop. And remember yesterday or 2 days ago what I said about whenever you see nested loops. So for j in range I plus 1, okay, so we don't have to start at I. We can start at the thing after I, which makes sense because if we go here, we'll see like, okay, we set whatever value. Let me refresh. 8, that's the smallest thing I've seen so far, but we don't need to like look at 8 again inside that loop. We can immediately go to the next place. If in list at j, so if the thing I'm looking at location j happens to be less than the smallest thing I've seen so far, just keep track of that thing and where we found it. So all this does is go over the contents of our list and keeps track of the smallest thing I've seen so far in the remaining part of the list that's unsorted. And then down here, this just says, okay, in list at min index is going to be in list at I. In list at I is minimum value. Great. Is this, I feel like this might be, there might be a bug in this code. Give me a second here to see if I'm going crazy or not. Because don't we have to, whatever, I'm going to take it, I'm going to test it to see if I'm going crazy. Don't need that anymore. Let's just go replace that sort. Great. I'll do this here. I guess it works. So my concern was, were we ever overriding, like, shouldn't we have to put min index, min list at I? Oh, no, I am doing it right. Okay, crisis averted. My concern here is a classic intro computer science bug, and somehow my brain wasn't firing on all cylinders enough to identify this thing. So we're swapping it. We can't simply just say in list at minimum index is, okay, we can't just say this, like in list at I is equal to the new minimum value, because we'll accidentally overwrite whatever was in list at I. So what this does is basically swap the two. So in list at min index, so where the smallest thing we saw was, we're going to put whatever was at location I there, just so it's moved out of the way. And then we put the actual new minimum value into in list at I. Crisis averted, there's nothing wrong here, we're happy, great. one of the things again to emphasize is that we don't need, the point is this specific implementation isn't what's important. What's important is this idea. What's the idea behind selection sort? Go through, select the smallest thing, put it in the beginning. Then find the next smallest thing, put it in its spot. Then the next smallest thing and put it in its spot, so on and so on. That's the idea behind selection sort. So let's do that geeky thing where we kind of analyze the algorithm. How many times, like worst case scenario, how many times is this going to have to run? And can we think of what is true about InList that will facilitate the best and worst case scenarios? What I mean here is, remember here, it was like when the list was sorted in order, when it got it, it actually like took n squared steps to do. But if it came in reverse order, but sorted in reverse order, it took only like n steps. So I'm asking the same question for selection sort. How many steps do we have to do in the worst case scenario, and what is the worst case scenario, and vice versa? So I'll give you a couple minutes. I'll give you to like 12:45 to see if you can think about it. Don't type in the chat or anything. Just take your time, think about it, and then we'll talk about it a little bit. I'm curious to see if anyone gets any ideas. So take a couple minutes to think about this. Maybe do that raise your hand thing if you think you know. Or you know what, I better maintain sharing, because in case you're not following along. But do that raise your hand thing if you think you figured out the answer. Don't say anything, just raise your hand. Just, I'm trying to get a pool of how many people got it. So there's one. I heard the ba-ding noise. Let's see. Oh, keep your hand raised if you think you got it. So we've got the one. Was there another one? Oh, it's kind of fun to do this. Whoa. You can even see like my mic thing bounce around too. How much time we got? 52. Oh, 7 more seconds. Okay. So, what are the ideas? Does anyone have any ideas? I see that Cole had an idea, but I'm curious, does other people, like, do they have any thoughts? You don't even need to be that confident in your answer. I'm just curious what people are thinking at this stage, because we don't need to be right. We just need to have an idea that we can then talk about. Oh, come on. Someone's got to give it a go. Can I bug Cole to do it then? Because you actually did raise your hand. Unfortunate for you. You can unmute yourself if you've got a mic and just make your suggestion. Thomas McDonald, I think you might be right? Wouldn't it have the same amount of work no matter what? Let's explore this idea. Yeah, that's what I was going to say. Okay, there we go. Fantastic. Raise your hand if you actually had that idea in mind, but you were just too shy to say it. 1, 2, 3. There you go. Okay, fantastic. So let's think about this. First, you know what? Maybe let's not think about what the worst case scenario is. Let's just look at the code and then go back to try to think about what the worst case scenario could be in terms of what in-list would have to look like. So for each time in the loop, wait, I guess I need to share my screen again. Oh, I'm so bad at this. Share. Let's see, I'm gonna open up Paint. So the first time through the loop, let's assume I've got like n things in that loop, okay? So we know the outside loop is going to run n times. N, okay? And so for the 0th time through the loop, or like when I is 0, how many times is this outside for loop going to run? Well, if it starts at I plus 1 to the end of the list, that's going to be n minus 1, right? So that's going to run like, okay, 1, 2, 3, 4, to n minus 1, right? Because if I starts at 0, then now the inside loop is going to be 1, and then it goes all the way to the end of the list. And the end of the list, okay, n minus 1. Actually, yeah, there we're good. So the next time through the loop, I is 1. So when I is 1, well, it's going to go like 2. I'm just going to draw it like this. Leave that like blank. 2, 3, 4, n minus 1. And then when I is 2, it's going to be like 3, 4, n minus 1. And then let's say we go down here to like n minus 1. And note, I'm doing the n minus 1 because we're 0-based indexed, you know? So if we go down here, how many times is this going to run? Well, n minus 1, actually like 0 times, right? Because it's not, let's do n minus 2. That's only going to run to n minus 1, right? And then when we get to n minus 1, well, we're going to run like there's nothing there. I'm just going to draw like a line to mean like nothing. Based on this, I mean, if the first time through the loop I'm running n, and then n minus 1, then n minus, or pardon me, the first time is going to be n minus 1, then n minus 2, n minus 3, to the end. You know what? If I look at this in reverse order, I'm going to be like, okay, it's 1 plus 2 plus 3 plus 4 plus 5, plus n minus 3 plus n minus 2 plus n minus 1. Raise your hand if that sounds familiar to anybody based on, especially anything we talked about last time. Come on, raise your hand. I want to see everyone's hand up. Do it. Do it. Keep going. There we go. Of course. It's an arithmetic series. So based on that, we also know, okay, chances are it's like n squared. But you'll also notice, like, I totally drew this as a square on purpose. But, you know, it's not really a square because it's like half that square. It's like this triangle. It's this part we don't care about. It's this part up here that we care about. But like we're doing like half of the square. So, you know, n squared kind of makes sense. Because it's half times n squared, but we don't really care about those coefficients. They don't matter that much. So n squared, there, great. Don't need to save that. Okay, yes, still shared. So, okay, what condition must be true? You know what? Like everyone said, I think you're right. It doesn't matter what the order is. No matter what, this is n squared. Because let's assume it comes in perfectly sorted order already. This algorithm, the way it's written, has to iterate over all the contents of that list to verify that the thing that it saw first is in fact the smallest thing. And if it comes in perfectly reversed order, it's going to, it has to search through and then find the smallest thing at the end either way. I mean, I suppose part of the problem is the algorithm will never know it's found the smallest thing until it's gotten to the end of that list. It's just a linear search, right? In the linear search, we don't know anything about that whole thing until we get to the end. So this one, the best and worst case scenario is n squared. Long story short, selection sort sucks, don't use it. But it's an algorithm, and it totally would work. Now bubble sort. Actually, no, let me go back. Raise your hand if, raise your hand if more or less you've used this algorithm before, where you've sorted something, you've gone through and just found the smallest thing, and then the next smallest thing, and then the next smallest thing to get your sorted thing. Only one person. I don't believe that. I don't believe that. Two people. I don't believe that for a second, but whatever, fine. Two people have used this algorithm. I'm willing to bet many of you have used this algorithm, whether you like it or not, despite being horrible. But isn't it funny how, look, I know you've all sorted things before, but you've probably never thought about sorting this much. You've never geeked out about, like, what are the operations I'm doing? What are the steps I'm doing in the algorithm of sorting? You've never thought about that. If you have, you're a nerd, and I'm glad you're in computer science because you'll fit right in. But chances are you haven't thought about it. But as soon as we start to think about it, we can start asking and answering the question, how good is this sorting algorithm? Is this sorting algorithm actually good? Is it bad? Could I do something different that's better? And so on. So there's a lot out there, but these are the couple that we like to talk about, especially when we start learning. All right, so bubble sort. Here's the idea. And here's another one that you may or may not have kind of done already. You start at the beginning of your list, and you compare the first two elements. I'm going to open up Paint again. Actually, no. Let's see if I can find bubble sort here. Bubble sort, bubble sort, bubble sort, bubble sort. Here we go. Perfect. This is what I want. Oh no, oh no. Okay. Look at the first two. If they're out of order, swap them. Look at the next two. If they're out of order, swap them. Keep going. Look at the next two. If they're out of order, swap them. They are, so we swap them. 6 and 8, well, they're not out of order, so we don't have to swap them. We can just carry on. There. 7 and 8, we got to swap them. And then 8 and 2, it looks like we're probably going to have to swap. And the last two we're going to have to swap. So there's a couple of things to note here. One, after doing one pass, is this list now sorted? No, absolutely not. A lot of people mess this up the first time they look at it. But another thing, too, look at this list. After doing one pass, we know that the biggest thing must be at the end of the list now. So although after one pass, we know that let me start again. After one pass, we're not sorted, but we know that the thing at the very end is in the position it must be. Now we must ask ourselves, how many passes do we need to do? This list is of some arbitrary size. How many times do we have to pass over this list and do this, like compare, 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 start over, compare, 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 start over, compare, and so on? How many times do we have to start over? Think about that. Raise your hand if you think you have an answer. Here's a hint. This is after the third pass. Okay, the third pass is now done. So let's start. Let's go here. Wait, who had your hand raised? Cole, Jared. All right, Jared. If you've got a mic, feel free to turn it on. Otherwise, type it in the chat. Jared, how many times are we going to have to do those passes? And you know what? I'm gonna make it even not n over 2, but I like what you're thinking. You're definitely in the ballpark. Does anyone else want to try? Put it into the chat. Oh, come on. I'll give you a hint. This looks like it's after 1, 2, 3, 4, 5 passes. And then boop, stop. N minus 1. N minus 1 is the correct answer. I would have also accepted n because minus 1, who cares? We're lazy and we're looking for ballpark answers. Jared was in the ballpark because n over 2, if we talk about this in complexity way, n over 2 is n. And so your ultimate answer would have been n because we don't care about the coefficients, that the fact that it's 1/2 times n. Anyways, Jared would have been right by accident. Kimberly would have been more precisely correct, but both correct, I suppose. So we have to do that pass n minus 1 times. So if we have to do a pass over a list of size n minus 1 times, any idea of how many steps we're going to have to do on this algorithm? Worst case scenario? So we need to do n minus 1 passes n times. Someone has to be able to do that math in their head. Someone type, you got to type it in the chat for me here. Give me something. Come on, no ideas? Let me see if I can go back to Paint. So I'm going to do, I need to go over that list of size n minus 1 times. I'm going to forget about the n minus 1 thing. So the 0th time through that list, I'm going to have to make like how many comparisons? So the 0th time, I'm going to make the first pair, the next pair, the next pair, all the way up to n minus 1, right? N minus 1 we can consider because like we're looking at pairs. The next time through, I guess I don't need to go to the end anymore, right? Because I know the thing is in the right position at the very end. So we look at 1, 2, 3, to n minus 2. And then 2, we'll look at 1, 2, 3, n minus 3, and we'll do that. I suppose n minus 1, the n minus 1th time. Well, I guess the n minus 1th time, there'd only be one cell left that we know must be in order. Anyways, this, I don't know, this looks kind of like a square to me. Someone type in the chat if they've got an idea now. Oh my gosh, I wasn't sharing my screen. Why didn't you say something? Let me, so disappointed in myself. There, this is what I was doing. For the 0th time, we have to do 1, 2, 3, to the n minus 1. And then the next time, 1, 2, 3, but we don't need to go to n minus 1, we go to n minus 2. And then the next time, n minus 3. All the way down to the n minus 1th time, where we only need to look at like that last thing, I suppose. Based on this, can you type in the chat what you're thinking? Come on, work with me here. Work with me. It's so much easier to participate online. All you have to do is type. I don't know, we're looking at that like half square thing. I don't know. Well, I'm hoping many of you have the answer in your head. And you're just too, can you show the whiteboard again? Whiteboard, well, it was the, here. I won't do the whiteboard because you guys are all bad and drawing appropriate things on the whiteboard, but I can show you my Paint, my Microsoft Paint example. And this is kind of that like half square. Just go with me that these things are. Here, maybe I can make this look a little better. There. It's kind of like half a square, right? What do we say? Someone's got to type in the chat. Do me a favor and we can end earlier. And by earlier, I mean just moments earlier. I don't know. To me, it looks like if I did the n minus 1 time, there'd be like 1. And then the next time there'd be 2, plus 3, plus 4, plus 5, plus plus n minus 3, plus n minus 2, plus n minus 1. I mean, does that look familiar? It should. It really should look very familiar. To me, it looks like it's going to be n squared. And let's go back to the code, because we didn't actually look at the code yet. Let's go look at some code. So it looks like it's n squared. And, you know, I'm seeing like loops and loops. Yeah. But we've actually made one small modification here that you wouldn't have been able to notice in the example we saw from Wikipedia. You wouldn't have noticed it here. So we've got like the nested loops. And this part here, it's basically doing the comparison of I and I plus 1. And if they're out of order, you do the swap. That's all that is. And down here, we've got this flag for swap something. Now, if I were to ask you the question, like, oh, it's the order of in list, does that order have an impact on how fast this algorithm will be? And this really depends on how we implement bubble sort. If we wrote bubble sort where it's guaranteed to do those like n minus 1 passes, because we know that after n minus 1 passes, the list is going to be guaranteed to be sorted. But look at what I'm doing here. I set something to swap something is true. And then I say, well, swap something. Immediately I set this flag to false. And what this flag is going to do is it's going to tell us, did we ever make a switch? And we start with no. When we start at the beginning, we never had to swap anything. And if we never swapped anything, that must therefore mean, like if we ever get to the end of the list and we never swapped anything, that must therefore mean that nothing was out of order. And if nothing was out of order, that must then therefore mean the list was sorted. So we start with true because we need to go this while loop, set our flag to false, and then this is the thing where we're going through, and if they're out of order, we go through each pair. If they're out of order, do the swap. And then as soon as we do a single swap, something becomes true. And it'll keep doing this until it compares every pair. If swap something is true, meaning we had to swap something, that means I don't know if the list is sorted yet. So we go back up, swap something is true, go in, reset it to false, do another pass. If we ever run this loop and we never flag or trigger this condition, swap something will remain false and we get out of it. Long story short, if in list comes in already sorted, it'll do one pass, it'll never set swap something to true, and then that's it. So with this implementation, best case scenario is it only needs to look at every pair, so like n things, and then we're done. If in list comes in already sorted. But the worst case scenario is going to be if things come in reverse order. So isn't it kind of funny how bubble sort and insertion sort, I think it was insertion sort, bubble sort, selection. If it wasn't obvious, I always mix up insertion and selection. But insertion, like the best and worst case scenarios, were the opposite for bubble sort. And I'm going to tell you something. All these sorts that we looked at, bubble, especially BOGO, which we looked at yesterday, but bubble, selection, insertion, they all suck really, really, really bad. They're all really bad sorting algorithms. And the sad part is they're probably the sorting algorithms that most people use when sorting things. Like if I have a stack of exams or something, it's probably what most people will use to sort. There are much better sorting algorithms that are going to be a lot faster, that if we have time before the end of the semester, we will get to. If not, we'll look at them next semester, and I'm going to guarantee you they're a lot more interesting and a lot more fun. But I'll end with this. There's one particular sorting algorithm that is king of all sorting algorithms, in my opinion, but it requires a very special condition. It requires that you don't actually care about getting the things you have sorted perfectly. You get them sorted enough that you're happy. And then suddenly you're guaranteed that the time it takes to sort is going to be like n. It's going to require n steps. And here's what you do. And a perfect example is sorting final exams. I want to sort my final exams such that they're in alphabetical order. That way, if someone wants to come and have a look at their final exam, you know, it's easy for me to find where they are. Otherwise, I got to look through a pile of 100 students. So I want them sorted. But you know what? That's going to be a pain in the ass. I don't want to sort all those things. So what I'll do is I'll just have them sorted such that all the A's come before all the B's that come before all the C's, and so on. What's in A might be out of order, but if it's sorted enough, you know, that however many are in the A bucket, we'll call it, will be relatively small that I can just, you know, thumb through them and be like, oh, okay, yeah, okay, there you are. So what I'll do is I'll create 26 different buckets, one for each letter of the alphabet. I'll take an exam, look at it. I have n exams, let's say, find out what your last name starts with, and put it in the proper bucket. And at the end, after I've gone through all of them, I'll have the things sorted mostly, but it's good enough for me. And this is a really good sorting algorithm if you don't need your things to be perfectly sorted. Technically, the number of steps this algorithm would use is n times k, where k is the number of buckets, because I have to do like, okay, I take this thing, the first exam, and then compare it to each of the buckets, and k, there could be k different buckets. In our case, it's 26. Technically, it's like n times k, but k should be a lot smaller than n. But anyways, that's a really good sorting algorithm. And we're over time, so thank you for those of you that showed up, and for those of you who are, and thank you for those that actually watched the YouTube video. But anyways, see you later. I'll stop recording, and have a good weekend. Bye.